Hello, pre-calc honor students. Here with 15.2, the multiplication, addition, and complement principles, and we're going to use these to solve counting problems. This is an essential skill for when we get to probability in chapter 16, because that's how we're going to determine probabilities. So let's see. The multiplication principle. If an action can be performed in n1 ways, and for each of these ways another action can be performed in n2 ways, then the two actions can be performed together in n1 times n2 ways. Let's see this in our first example. You have 4 sweaters. So let's say you got your sweaters here. And you've got a blue one and a brown one and a gold one and a striped one. And you got 2 pairs of jeans. And so let's say you got your blue jeans and your black jeans. So this is the jeans column. Blue or black. Blue or black for each one of these. Blue. Oh, there's the blue and gold person. Black. Blue. Black. So you end up with a total of 8 possibilities. That's what we get for answer, 8. Because basically, you had 4 choices for the first action, and then 2 choices for the second to get you a total of 8 choices. In how many ways can 8 people line up in a cafeteria line? Well, let's make space for them. Here's our cafeteria line. Can't wait to get at that mac and cheese. So here's the first person in line. There's 8 choices because you have 8 people. But now you've used up one of your choices, so now you only have 7, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. So it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which ends up being, as we guessed, 40,320. Wow. Now, a shortcut for this last problem is to use n factorial, and this was essentially 8 factorial, as you recall, right? 8 factorial equals 40,320. Let's go through factorials again. Oddly enough, 0 factorial is 1, and for some of the definitions we do next section, you're going to need that. 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2, so that's 6, 4 factorial, 4 times the previous one. So notice, rather than going 4 times 3 times 2 times 1, I could say 4 times 3 factorial. 4 times 6 is 24. So same thing with 5 factorial. 5 times 4 factorial. 5 times what we just came up with, and that's where you get 120. 6 factorial. 6 times 5 factorial. 6 times 120. 720. And then you get 840, and then you get 8 factorial of 40,000. So it really grows rapidly. So, in fact, a recursive definition for n factorial is to take n factorial as n times the previous factorial, n minus 1 factorial. Now, there's actually something called the gamma function, where you can actually do a half factorial and so forth. You might want to explore that in your calculator. It's something the 85s used to do, the 86s, but no, the 89s don't so much. But they do have the gamma function, so you can look that up. How many license plates can be made by using 2 letters followed by 3 digits? Well, make room for your 2 letters. So these are our letters. And we're going to have 2 of them. And then we're going to have some digits followed by 3 digits. And we're going to multiply all these together. We have 26 letters, and we don't use them up. So, and then there's 10 digits, 0 through 9. 26 squared times 26 times 10 times 10 times 10, and that works out to be this huge, I don't think I need a whole page for this, 26 squared times 1,000. Let's check out 26 squared. 26 squared. 26 squared is 676. So 676,000. Just as I thought. Now, the addition principle. If 2 actions are mutually exclusive, and the first can be done in n1 ways and the second in n2 ways, then one action or the other can be done in n1 plus n2 ways. So that's basically what we're doing here. We're counting up the number of elements in this set, the number of elements in this set and just add them up. Because it's not a chain of events, it's an either-or situation. Now notice we don't have to subtract off the overlap because I've made these mutually exclusive, means no overlap. The intersection of A and B is equal to 0. So in Morse code, the letters of the alphabet are represented by the sequences of dots and dashes. For example, dot dash represents the letter A and dash dash dot represents the letter G. Show that sequences of no more than it should be 4 symbols, dots and dashes, are needed to represent all of the alphabet. Well, let's take a look at the cases we got here. We can either have it says no more than 4, so that means it could either be 1 symbol or 2 symbols or 3 symbols or 4 symbols. These are mutually exclusive events, so we can just add up the number we get in each. So let's start with the 1 symbol possibilities. That's either dash or dot. Okay, so that we got 2 from that one. Let's try the 2 symbol ones now. 2 symbols could be dash dash, dash dot, dot dash, dot dot. So we get 4 from that. I think you see where this is going. 3 symbols would be dash dash dash, dash dash dot, dash dot, dash, dash dot, 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 dash dash, dot, dash dot, 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 dash, dot, dot, dot. 8. Does this remind you of anything? Come on, you remember, way back in the beginning of the year. 4 symbols. Dash, 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 dot. Dash, dash, dot, dash, 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 dot, dot. Dash, dot, dash, 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 dot, dash, dot. Dash, dot, dot, dash, dash, dot, dot, dot. Dot, dash, dash, dash. Dot, dash, dash, dot. Dash, dot, dash, dot, dash, dot, dash, dot, 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 dash, dash, dot, dot, dash, dot, 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 dash, dot, 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 dot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what are we up to so far? We got 2 and 4 and 8 and 16, 30. That covers the alphabet. Notice if we had stopped earlier, alphabet of 26 letters. If we'd stopped with only 3, that wouldn't have done it. That would have been only 14. So here comes the complement principle. If A is a subset of the universal set U, then the number of elements in A is the number of elements in U minus the number of elements not in A. So sometimes it's easier to count a set by counting what it's not, and then subtracting that from the whole. So you've got your set A here, here's not A out here. It looks like it might be easy in this diagram to count A, but sometimes the set of not A is smaller. So find the number of 4-digit numbers containing at least 1 5. So that would be all the 4-digit numbers minus the ones that do not have at least 1 5. Because this can be easier to count, because not have in at least 1 5 means no 5s. And all the 4-digit numbers, to do a 4-digit number, you got to make sure you don't start with a 0. So you only have the choice of 1 through 9 here, so that's 9 choices. But then we can pick 0 through 9, so we got 10 choices for each of these. So you got 9,000 4-digit numbers. Now for no 5s, you got to change your thinking a little bit here now. That means we only have 8 choices here because we can't use a 5 or a 0. So we have basically, we can put 1, 2, 3, 4, 6, 7, 8, 9. That's how we got 8 choices for the first digit. And then we have 9 for each of these because we can't use a 5. So 8 times 9 cubed works out to be 5,832. And then that works out to be 9,000 minus 5,832. Zip, 9, 9, 10, 8. I think I'm going to beat the calculator on this one. 2,100. 3,168. Oh, a little haste there. A little haste there, Flange. There you go. 3,168. Now notice how much more arduous this would have been if we had taken the tack of containing at least one 5 as it contains 1 5 or 2 5s or 3 5s or 4 5s. Now the 4 5s would have been easy, but the 1 5 and the 2 5 and 3 5, you'd have to figure out where do the 5s go and so forth. I present that to you as a nice extra credit challenge, doing it the longer way. Okay, Flange out.